I want you to just close your eyes for just a moment. Try to, strip away the room you're in right now, the device you're listening on, the ambient hum of modern life. Picture yourself standing entirely alone in the center of this vast ancient desert.
Yeah, it's absolute isolation.
Yeah, exactly. The sun has long since bled away over the horizon. You've got the residual heat of the day rising off the cooling sand, and the silence around you is just so absolute, so dense, it almost rings in your ears. And now you tilt your head back.
And it's not the sky we're used to.
Right, no. Above you is not this pale, washed out, artificially lit sky of a modern city. It is this dome of absolute crushing darkness, and it's just crowded with a violent, magnificent spray of starlight. It's a terrifying ocean of light, ancient and completely indifferent.
It really is an ocean.
It is. And standing there, you are struck by this visceral, almost physical weight bearing down on you, which is the exact same weight that every single human ancestor felt when they looked upward into the dark. In that stillness, you find yourself whispering the absolute oldest, most fundamental questions our species has ever dared to ask. Where did all of this actually come from?
Right.
What exactly is this invisible river we are all trapped in, the one we call time? And if you were to travel outward forever, past the furthest stars, would you eventually hit a wall? Does reality actually have a physical edge?
Which is really, it's the only place we can truly begin. Because those earliest cosmic questions, the ones that kind of haunt us in the dark, they weren't written in the formalized language of mathematics.
They weren't from a lab.
Exactly. They weren't tested in sterile laboratories. They were born out of raw, unfiltered awe. When you look at the night sky from that desert, you aren't just, intercepting photons that have traveled for millions of years across a frozen vacuum. You're literally participating in the very origin of human curiosity.
We've always been trying to map things out.
We have. We have always been a species desperate to locate ourselves in the dark. The tone of our inquiry has obviously evolved into, complex equations and orbital telescopes, but the underlying drive, that profound, almost desperate need to map the territory of existence, that remains completely unchanged.
And mapping that immense territory is our singular mission today. We are taking the source material provided in this fascinating text, The Unfinished Universe, and we're using it as our compass. This deep dive is going to be an immersive journey through the architecture of space, the flow of time, the curvature of gravity, and perhaps most crucially, the absolute limits of human knowledge.
It's quite a journey.
It's massive. We're going to trace the fragile thread of human understanding from those ancient desert campfires right through the mechanical clockwork of the scientific revolution, all the way to the jagged edge of black holes and the quantum dawn of reality itself.
But before we take a single step forward into that dark, we have to establish the primary ground rule for this entire expedition.
Oh, this is the hard one.
Yeah, it's a rule that you might find deeply uncomfortable. And it is simply this: the universe is under absolutely no obligation to make sense to you. It is under no obligation to match human intuition.
Which is, that's a tough pill to swallow. We really like to think our common sense is a reliable tool for decoding reality.
Sure, because it is reliable for surviving. Our brains evolved to help us hunt, gather, and avoid predators on relatively warm rock.
Right.
Our intuition was forged to deal with slow-moving objects, weak gravity, and incredibly short local distances. Our neurology is profoundly local. So when we start probing the extreme frontiers of the cosmos, the incredibly fast, the infinitely dense, the subatomically small, our everyday common sense doesn't just struggle, it completely shatters.
It just fails us.
Completely. If we want to understand the universe as it actually is, we have to learn to trust the observational evidence, even and especially when it tells us something that feels entirely, absurdly impossible.
So let's anchor ourselves back in that desert for a minute. Long before we had orbital observatories detecting invisible radiation, long before particle colliders smashing atoms to pieces, we just had the sky. And I find it fascinating that humanity's very first scientific breakthroughs weren't actually about understanding the mechanisms of the universe.
No, not at all.
They were purely about the recognition of patterns. We learned regularity thousands of years before we understood the machinery behind it.
And that distinction is the bedrock of all astronomy. Our ancestors had no conception of what the moon physically was, right? They didn't know it was a dead sphere of rock locked in gravitational embrace with Earth.
Of course not.
But they realized that its shifting phases could be tracked, predicted, and used to measure the passage of months. They noticed that among the thousands of fixed stars, a tiny handful seemed to wander across the sky.
The wanderers?
Yeah, we call them planets now,
Yeah.
from the Greek word for wanderer. They realized that eclipses which for millennia were perceived as terrifying, unpredictable omens of divine wrath. They actually operated on a rigid mathematical schedule.
And what the source text makes beautifully clear is that this wasn't just some isolated phenomenon. It wasn't one culture hoarding all this knowledge. The sky was humanity's first massively open source archive shared globally.
Absolutely.
You have Babylonian astronomers carefully pressing cuneiform records of planetary movements into wet clay tablets, accumulating these vast generational data sets. You have Greek natural philosophers taking a monumental philosophical leap, stepping away from mythology and asking, for the first time, if the heavens could be explained purely by geometry.
And that mathematical torch was carried and amplified across the whole world. I mean, Indian mathematicians spent centuries refining the trigonometry required to calculate planetary orbits with staggering precision.
Which is just wild to think about without computers.
It's incredible. And Chinese court astronomers maintain meticulous, unbroken records spanning thousands of years, tracking these fleeting phenomena like comets, supernovae, eclipses, things that Western astronomy largely ignored at the time.
Right.
And during the Islamic Golden Age, scholars didn't merely preserve and translate ancient Greek texts. They relentlessly tested them against the night sky, they corrected the massive errors, and they pushed the mathematical frameworks to entirely new heights.
But all of this intense generational observation eventually birthed a massive psychological crisis, right? Because every successful prediction, every painstakingly refined table of star positions, it just sharpened the ultimate lingering puzzle. Is the universe actually arranged around us?
The big question.
Yeah. Or are our human senses deceiving us, placing us at the center simply because of where we happen to be standing?
That is the friction that ignited the scientific revolution. The transition from a geocentric universe where the Earth is the fixed, unmoving center of all creation to a heliocentric one, where the Earth is just another rock in motion. That is arguably the greatest psychological trauma our species has ever willingly endured.
I want to pause on that word, trauma, because I think it's perfect. Imagine the sheer existential vertigo of being told that the solid ground beneath your feet, which your every physical instinct insists is perfectly, fundamentally still, is actually hurtling through a lightless vacuum at tens of thousands of miles an hour.
It defies every sensory input you possess.
It totally does.
And the source points out that this revolution wasn't a clean, linear march of isolated geniuses having sudden epiphanies. It was a messy, agonizing relay race. I mean, Copernicus had the mathematical audacity to reorganize the solar system, putting the sun in the middle.
Right, a huge leap.
Huge. But he was still trapped by ancient philosophical baggage. He believed celestial orbits had to be perfect circles because circles were divine. And since the actual orbits aren't perfect circles, his math didn't quite work. It was clumsy.
Then you bring in Tycho Brahe, who is just a legendary figure to me. Before the invention of the telescope, Brahe spends his life building massive, building-sized brass instruments to measure planetary positions with unmatched, naked-eye precision. He mapped the night sky with a fanatic's devotion.
And Brahe's obsessive data became the inheritance of Johannes Kepler.
Right.
Kepler was this deeply devout mathematician who spent years in absolute agony trying to force Brahe's data to fit the perfect divine circles of Copernicus, and it just wouldn't fit. Kepler eventually had to endure the heartbreak of realizing the heavens were not geometrically perfect. Planets don't move in circles, they move in stretched out, imperfect ellipses.
Which fundamentally shattered the ancient Aristotelian idea of perfect crystal spheres holding the planets in place. And then Galileo points his newly modified telescope at the sky and completely dismantles the illusion of celestial perfection.
The first time we really looked close.
Yeah, he sees jagged, shadow-casting mountains on the moon. He sees moons orbiting Jupiter, which prove definitively that not everything in the universe revolves around the Earth. He observed the phases of Venus, which is only geometrically possible if Venus orbits the sun.
And all of this disparate, terrifying new data culminates with Isaac Newton. Newton is the intellect who finally bridges the heavens and the earth. He realizes that the force making an apple fall from a branch in an orchard is the exact same invisible force tethering the moon in its orbit around the earth.
Universal gravitation.
Exactly. He gave us one universal law of gravitation. Suddenly, the chaotic, terrifying universe became a calculable clockwork machine. If you knew the positions and speeds of the parts, you could calculate their entire past and predict their entire future. Determinism was born.
But here's where we need to rethink how we view scientific progress. I want to look closely at a vital analogy from the text about how we map reality. Because when people hear that Newton's laws were eventually superseded by Einstein, They often assume Newton was just a fool who got it all wrong.
which is a fundamental misunderstanding of how physics operates. Picture the challenge of understanding the universe as trying to navigate a vast, endlessly complex alien landscape while trapped in absolute darkness. You cannot see the terrain. A scientific theory is not the landscape itself. A theory is just a map you draw based on what you can feel in the dark.
So you're wandering blindly, and you bump into a landmark, say the way light refracts or the way a planet accelerates. You chart it. You bump into another landmark, and you draw a mathematical line connecting them.
Yes. A successful scientific map connects all those known, verified landmarks with a coherent internal geometry. It tells you where the next hidden landmark ought to be, and the hallmark of a true scientific map is that it includes explicit instructions for how to prove the map wrong.
That's the key.
It is. In cosmology, our landmarks aren't mountains or rivers. They are the emission spectra, the ticking of atomic clocks, subatomic particles, and the statistical clustering of galaxies.
So when a new map comes along, when Einstein arrives, it doesn't mean Newton's map goes in the trash. Science advances by nesting successful approximations inside deeper, more encompassing explanations. Newton's map of gravity is still incredibly powerful. We literally still use Newton's equations to calculate the orbital trajectories of rovers we send to Mars.
Newton's map is perfectly accurate as long as you stay within a specific province of reality where speeds are relatively low and gravity is relatively weak.
Right.
But his map contained a hidden, deeply ingrained assumption. Newton assumed that the clockwork universe played out on a rigid, unmoving stage of absolute space and absolute time. He believed, as did everyone else, that 1 second ticking away for you on Earth was exactly the same second ticking away for an observer on the other side of the cosmos.
It makes sense intuitively.
Totally. He believed a meter was a meter, everywhere and always. Time and space were just the empty, passive theater where the events of reality took place.
And that rigid, absolute stage held up beautifully for over 2 centuries. But then, as the text describes it, a single beam of light exposed the fatal cracks in the floorboards. We need to completely unpack the illusions of absolute time and space. We are stepping into the mind of Albert Einstein and the birth of special relativity.
Special relativity fundamentally stems from 2 strict, unforgiving demands about how reality must operate. The first is the principle of relativity. The laws of physics must take the exact same mathematical form for any observer moving at a steady, unaccelerating speed. If you are in a spaceship gliding smoothly through the void, no physical experiment you can perform inside that ship will tell you if you are moving or standing still.
The second demand is the one that completely breaks our everyday intuition. It is the realization that the speed of light in a vacuum about 186,000 miles per second is always measured to be exactly the same, no matter how fast you're moving toward or away from the light source.
And that violates everything we understand about how velocities work in the macroscopic world. I mean, if you are standing on the sidewalk and a car drives past you at 50 miles an hour, and someone in the car throws a baseball forward at 50 miles an hour, you see the baseball moving at 100 miles an hour.
Right. Velocities are additive.
Exactly. But light absolutely refuses to behave this way.
So if I am flying in a spaceship at half the speed of light and I turn on a flashlight pointing forward, I see the beam of light speed away from me at exactly the speed of light. But if you are standing on a planet watching me fly by, you do not see that light moving at 1.5 times the speed of light. You also measure it moving at exactly the universal speed limit.
And this creates a catastrophic logical paradox for classical physics. Speed is just distance divided by time. If we are both moving at vastly different speeds, but we both measure the exact same speed for that beam of light, then something else in the equation has to give.
Something has to stretch.
Yes. The rigid stage of reality has to warp. To preserve the absolute constant speed of light, nature adjusts the very quantities we thought were immutable. Space and time become malleable. If I am watching you speed past me in that spaceship to make the math of the universe balance, I will literally measure your clock ticking slower than mine. Time dilates.
It's wild.
And I will measure the physical length of your spaceship contracting in the direction of your motion.
This is where I have to push back, or rather, where I need to highlight the profound existential horror of this concept. Let's abandon the classic train metaphors for a moment and look at the absolute death of a universal now. If time is relative to the observer's speed, then my present moment is completely different from your present moment if we are moving relative to each other.
That is the shattering revelation. Simultaneity is an illusion. Imagine 2 supernovas exploding at opposite ends of a galaxy. From my perspective, standing still relative to the galaxy, I see them explode at the exact same instant. I say they were simultaneous. But you are flying through the galaxy at a massive speed toward one supernova and away from the other. Because the speed of light is constant, the light from the supernova you were moving toward reaches you first. In your reference frame, one exploded years before the other.
So who is right? Which event actually happened first in the grand timeline of the universe?
You are both entirely correct in your own reference frames. There is no grand timeline of the universe. A universal now does not exist. Space and time are not separate, independent containers. They are inextricably woven together into a single four-dimensional fabric called space-time.
It's just a completely different paradigm.
It is. Every object, every observer draws their own unique slice of time through that block of reality based on how they move through space. It also led Einstein to the realization that mass and energy are essentially interchangeable currencies, bound together by the equation E equals mc squared. The energy of motion literally adds to the mass of an object.
But special relativity had a major limitation, didn't it? It only applied to smooth, steady, unaccelerating motion. It completely left gravity out of the picture. Einstein spent the next decade in an agonizing intellectual struggle trying to weave gravity into this new, flexible fabric of space-time. And it all finally clicked for him with what he later described as the happiest thought of his life. A brilliant, simple thought experiment about a falling elevator.
Right, imagine you are locked inside a windowless elevator car. Suddenly the cable snaps, and you are in a state of absolute free fall down the shaft. During that fall, if you let go of your keys, what happens?
They float.
Exactly. They don't fall to the floor of the elevator. They hover right next to your hand because you, the keys, and the elevator are all accelerating downward at the exact same rate. Inside that closed box, you feel entirely weightless. Einstein realized that you cannot perform any physical experiment inside that box that would distinguish between being in free fall in a gravitational field and floating in deep space far away from any gravity.
Which means acceleration and gravity are fundamentally the same experience. That is the equivalence principle.
Yes, and from that deceptively simple realization, Einstein entirely rebuilt our map of the universe. In general relativity, gravity is no longer an invisible tether pulling objects across a distance the way Newton imagined. Instead, mass and energy physically warp the geometry of space-time around them. And in turn, that curved space-time dictates how matter and light move.
Okay, we need a better analogy here. The old textbook metaphor is placing a heavy bowling ball on a rubber trampoline, creating a dip, and rolling a marble around it. But that always bothered me because it uses the Earth's gravity pulling the bowling ball down to explain gravity, which is circular logic. It doesn't really explain the mechanism.
You're completely right. The trampoline is deeply flawed. Instead, imagine space-time not as a flat sheet, but as a three-dimensional rushing river. The water of this river is the coordinate grid of space and time itself. Massive objects, like a star or a planet, behave like massive drains in this river. They actively drag the geometry of space inward toward their center. The heavier the object, the faster the river of space flows toward it.
So when the Earth orbits the Sun, it isn't being pulled by an invisible string. The Earth is simply trying to move in a straight line through space, but the Sun's massive presence is warping the coordinate grid of space into a circle. The Earth is swimming straight, but the river itself is curved.
Exactly. Gravity became purely geometry. And this wasn't just beautiful, elegant mathematics. It made hard, testable predictions that proved Newton's map incomplete. It perfectly explained a tiny nagging anomaly in the orbit of Mercury, a perihelion precession that Newton's laws simply couldn't account for.
It solved a real mystery.
It did. It predicted that intense gravity would literally stretch the wavelength of light, redshifting it. And most famously, it predicted that the mass of the Sun would curve the river of spacetime so severely that starlight passing near it would be visibly deflected from its straight path.
Which was spectacularly proven during the total solar eclipse of 1919. The astronomer Arthur Eddington traveled to the coast of Africa, photographed the star field behind the eclipsed sun during the darkness of totality, and proved that the stars appeared to have shifted their positions. The starlight had followed the curve of space-time around the sun exactly as Einstein's equations demanded. The map worked.
And it isn't just space that curves. Time itself bends under gravity. The source notes that modern atomic clocks, which measure time by the vibrations of atoms, can actually detect time passing at slightly different rates depending on altitude.
Wait, really? Just based on altitude?
Yeah. Because gravity is slightly stronger closer to the center of the Earth, The river of time flows a tiny bit slower at your feet than it does at your head. You are literally aging at different rates depending on where your body is in the gravitational gradient.
It is a profound, beautiful system. But the danger of mathematics is that once you accept the premises, you have to follow the equations to their absolute extreme conclusions. If space-time is a flexible geometry that can ripple and warp, the math permitted environments where that curvature becomes infinitely steep. It predicted places where the river of space-time flows inward faster than the speed of light.
And that brings us to the dark shore. We are talking about black holes.
To understand the sheer violence of a black hole, we have to look at the life cycle of a massive star. For billions of years, a star is locked in this delicate, agonizing balancing act. You have the crushing inward pull of gravity trying to collapse the star's immense mass into a single point. And fighting against that, you have the explosive outward pressure of nuclear fusion burning in the core, pushing the star apart.
But a star's fuel is finite. Eventually, the core burns through its hydrogen, its helium, its carbon, all the way up to iron. Fusing iron consumes energy instead of releasing it. The nuclear fires instantly go out. The outward pressure stops. In a fraction of a second, gravity definitively wins.
And that the star is massive enough, there is no physical force in the universe. No atomic repulsion, no quantum pressure strong enough to halt the collapse. The entire mass of the core compresses into a region so impossibly small and so infinitely dense that it creates what we call an event horizon.
Yeah, we must be incredibly precise here, as the source text insists. An event horizon is not a physical solid surface. You couldn't land a ship on it. You couldn't touch it.
It's a causal boundary. Returning to our river analogy, the event horizon is the exact perimeter where the waterfall of space-time is plunging inward at exactly the speed of light. Because nothing in the universe can travel faster than light, nothing can swim upstream against that current. Once you cross the event horizon, the geometry of space and time is so violently warped that every possible path forward, every direction you could possibly point your thrusters, every future you can logically experience, points inevitably inward toward the center. Escape isn't just difficult because gravity is pulling hard. Escape is geometrically impossible. The future only exists inward.
And yet, if they are perfectly dark, if not even light can swim against the current, how do we know they are there? How does a completely invisible object announce its presence across the vastness of an entire galaxy?
Because while the horizon hides the interior, the space immediately outside a black hole is an engine of absolute terrifying chaos.
Correct. If a black hole is feeding on a nearby companion star, the gravitational shear strips the gas away, pulling it into a swirling, chaotic accretion disk. As that material spirals closer to the event horizon, the crowding and the immense gravitational acceleration cause the gas to experience massive friction. It heats up to millions of degrees, glowing with fierce radiation, blasting out powerful X-rays that can be seen across the universe.
So it's basically a lighthouse.
A very dangerous lighthouse. We can also detect black holes by watching the gravitational influence they exert on stars, orbiting them stars, whipping around an invisible center of mass at impossible, terrifying speeds.
So according to general relativity, the event horizon is the ultimate one-way door. Matter goes in, nothing comes out. Absolute eternal silence. But then as the text explores, we reach a point in history where our two greatest scientific maps crash into each other and catch fire. Because Stephen Hawking looked at the dark shore of the black hole and realized that the bizarre rules of quantum physics absolutely refuse to let that horizon remain completely black.
This is arguably one of the most brilliant and disruptive insights in modern theoretical physics. Hawking asked a question that sounds absurd on its face. Can empty space have a temperature?
Well, common sense says no. Empty space is empty. It's nothing.
But according to quantum field theory, the vacuum of space is never truly empty. It is not an absolute void. It is a roiling, probabilistic sea of energy where pairs of virtual particles, matter and antimatter, are constantly popping into existence, borrowing a tiny debt of energy from the vacuum, and then immediately colliding and annihilating each other to repay the debt. This happens everywhere, all the time.
But Hawking imagined what happens when one of these virtual particle pairs pops into existence right on the razor's edge of an event horizon.
Exactly. If this quantum fluctuation happens precisely at the boundary, one particle can get swept over the falls, sucked into the black hole, while the other particle is stranded just outside the event horizon. Suddenly deprived of its partner, the stranded particle cannot annihilate. It is forced to become a real particle, and it escapes into space as thermal radiation.
To a distant observer, the black hole appears to be glowing. It is emitting heat. And because that radiation carries energy away into space, and Einstein taught us that energy and mass are the same thing, the black hole is literally losing mass. It is evaporating.
Hawking radiation.
Yeah.
Now, we must clarify that for stellar mass black holes today, this temperature is incredibly close to absolute zero, far colder than the ambient background temperature of space, so they are absorbing far more background radiation than they emit. They aren't shrinking noticeably right now.
Right, they're still growing.
Yeah. But over unimaginable trillions of years, timescales, when the universe goes dark and cold, they will evaporate entirely. And that creates a massive catastrophic problem for physics. It creates the information paradox.
I want to spend time on this because it isn't just a quirky math puzzle. It is a crisis of reality. Let's visualize the information paradox. The entire foundation of quantum mechanics relies on the absolute law of unitarity. The idea that information about a physical system cannot be fundamentally destroyed. If you know the exact quantum state of something, the spin, the momentum, the charge of all its particles, you should theoretically be able to track its entire past and predict its entire future.
So imagine a black hole forms from the collapse of a very specific, unique star. Then, over its lifetime, it swallows a planet, it swallows a clock, a beam of light, and let's say it swallows an entire hard drive perfectly encrypted with distinct, unique data. According to general relativity, all that information is safely locked inside the event horizon. It's hidden, but it still exists.
But according to Hawking's quantum calculations, the black hole slowly evaporates away by emitting thermal radiation. And here's the terrifying paradox that Hawking radiation is completely featureless. It is random. It is just uniform heat. It contains no trace of the specific quantum information of the star, the planet, or the encrypted hard drive that fell in. So when the black hole finally evaporates completely into a flash of light, leaving nothing behind, where did all that unique quantum information go?
It seems to have been erased from the universe. And that is deeply alarming. It's like taking a highly detailed, beautifully encrypted message, running it through a shredder, and then burning the shreds. If you gather every single molecule of ash, every wisp of smoke, every photon of light emitted by the flame, quantum mechanics insists the information of the message is technically still there in the universe, just incredibly scrambled. Give it a big enough computer, you could reverse the physics and read the message.
But a black hole isn't a fire. If the black hole evaporates completely and leaves behind only uniform, random thermal radiation, it's like burning the message and being left with ash that has literally forgotten it was ever paper. The physics are completely irreversible.
And that paradox is a glaring neon warning sign. It tells us that our map of general relativity, which governs the incredibly massive and dense, and our map of quantum mechanics, which governs the incredibly small and probabilistic, are fundamentally incompatible.
Yeah.
When you try to overlap those two maps at the event horizon of a black hole, the mathematics literally break down into infinities and nonsense.
To understand why these maps refuse to overlap, we have to step behind the quantum veil. We have to shrink our perspective down to the smallest possible scales where nature completely abandons the clockwork determinism of Newton and Einstein and starts offering us a chaotic casino of probabilities.
The quantum realm is profoundly alien because it defies every intuition we've built interacting with the macroscopic world. In classical physics, a particle is like a billiard ball. It has a definite position, a definite speed, and a definite trajectory. But in quantum mechanics, a particle isn't a solid point. A system is represented by a wave function, a mathematical probability state that can contain superpositions.
Meaning a particle can exist in multiple possible states or multiple possible locations simultaneously until it is forced to interact with something or be measured. It's not that we just don't have good enough microscopes to know where the particle is. It's that the particle itself fundamentally does not have a definite location in the fabric of reality until the act of measurement forces it to pick one.
That is the core of Heisenberg's uncertainty principle. It's vital to understand that this is not about having clumsy scientific equipment. It is a fundamental, inescapable limit built into the architecture of nature. You cannot simultaneously know a particle's exact position and its exact momentum. The more sharply you pin down exactly where it is, the more uncertain its speed and direction become. The underlying nature of reality is inherently probabilistic, not deterministic.
And then there is quantum entanglement, a concept so bizarre that Einstein famously derided it as spooky action at a distance. He refused to believe it was the final answer.
Entanglement occurs when particles interact in such a way that their quantum states become permanently linked, regardless of distance. If you measure the property of one entangled particle here on Earth, you instantaneously know the property of its partner, even if that partner is currently on the other side of the Andromeda Galaxy.
Which seems to violate the speed of light. It feels like they are communicating instantly.
It does feel that way, which is why Einstein hated it so much.
Yeah.
But it doesn't actually violate relativity because it doesn't allow you to send controllable information faster than light. You can't use it as an instantaneous telephone, so causality is preserved. But it absolutely proves that the quantum universe is deeply, non-locally connected in ways that classical physics simply cannot accommodate.
So we have this microscopic world of chaotic probabilities, superpositions, and deep uncertainty. But the text asks us to scale this quantum chaos up. What happens when we apply these microscopic concepts to the entire universe? Because general relativity tells us that space itself is dynamic. It can warp, and crucially, it can expand.
In the 1920s, observations by Edwin Hubble and other astronomers revealed a startling truth. The distant galaxies are all receding from us, and the further away they are, the faster they appear to be moving away. But we have to be very careful with our language here. The galaxies aren't moving through space like shrapnel from a bomb. The metric of space itself is expanding, stretching out, carrying the galaxies with it.
And simple logic dictates that if the universe is expanding today, it means it was smaller yesterday. If you play the cosmic movie in reverse, the universe gets denser, hotter, and more compact. If you rewind it far enough, some 13.8 billion years, you reach a phase where the entire observable universe was crammed into a space smaller than a single atom.
This is the hot Big Bang. And we need to explicitly correct a massive public misconception here. The Big Bang was not an explosion into a pre-existing empty void. It was an expansion of space itself, occurring everywhere all at once. There is no center of the Big Bang, just as there is no center to the surface of a balloon as it inflates.
And we have profound, irrefutable evidence for this early state. We can run the math on the temperatures and pressures of that early, dense universe, calculate the exact abundance of light elements like hydrogen, helium, and lithium that would be forged in that primordial furnace, and our modern observations perfectly match those predictions.
But the most spectacular and direct piece of evidence is the ultimate cosmic fossil, the cosmic microwave background, or CMB.
Let's paint a picture of this fossil. Imagine the early universe just a few thousand years after the expansion began. It is a super hot, incredibly dense, opaque fog of plasma. Light cannot travel freely. Photons are constantly bouncing off a chaotic soup of free electrons. The universe is glowing, but it is completely impenetrable.
But as space continues to expand, it cools. Roughly 380,000 years after the expansion began, the temperature dropped just enough to about 3,000 degrees Kelvin for those free electrons to finally slow down and bind with protons, forming the very first neutral atoms of hydrogen.
The fog instantly lifted. The universe became transparent.
Yes. And that first burst of light, the sheer blinding radiation released at that exact moment of transparency, has been traveling freely through the expanding universe ever since. Over the last 13.8 billion years, as the fabric of space stretched, those light waves were physically stretched with it, cooling down and lengthening into microwaves. Today, that radiation surrounds us completely. If you tune an old television to an empty channel, a small percentage of that static is actually the residual heat of the Big Bang. It is a faint glow coming from every direction in the sky, a literal baby picture of the cosmos.
It's an incredible achievement to have captured that image. But here's the question that really causes friction, the problem that theorists had to scramble to solve. When we look at that baby picture, the CMB, the temperature is incredibly uniform. It is almost exactly the same temperature in every single direction we look, down to a tiny fraction of a degree. But if the universe started in a state dominated by quantum chaos and probabilistic uncertainty, how did it yield a cosmos that looks so incredibly smooth and flat on the largest scales? If the opposite sides of the observable universe are so far apart that they could never have exchanged heat or information at the speed of light, why do their temperatures match perfectly?
That is the famous horizon problem. And to solve it, theorists propose an event that occurred in a fraction of a heartbeat that forever shaped the architecture of the cosmos. We need to introduce the three great unseen forces of modern cosmology. We are stepping into the invisible architecture and the accelerating dark, starting with cosmic inflation.
What could possibly happen in less than a heartbeat to organize the chaos into the universe we see today?
Inflation proposes that in the absolute earliest fraction of a second after the Big Bang, we are talking about 10 to the minus 36 seconds, the universe underwent an extraordinarily violent, exponential period of accelerated expansion. The fabric of space stretched vastly faster than the speed of light.
Which, again, doesn't violate relativity because it's the coordinate grid of space itself expanding, not objects moving through space. Space can stretch as fast as it wants.
Precisely. And this rapid, violent stretching solves the horizon problem elegantly. Why is the temperature uniform everywhere in the CMB? Because before inflation occurred, all those regions of space were crammed close enough together to exchange heat and reach an equilibrium. They were neighbors. Then inflation suddenly ripped those localized regions billions of light years apart.
And it also explains why the universe appears geometrically flat on large scales. If you take a small, wrinkled, curved balloon and suddenly inflate it to the size of the Earth, the surface will look perfectly flat to an ant walking on it. Inflation stretched out the primordial curvature of space until it appeared completely flat to our instruments.
But perhaps the most beautiful consequence of inflation is how it explains the structure of the universe. It takes those microscopic, chaotic quantum fluctuations in the early vacuum, those tiny probabilistic ripples in energy we talked about, and freezes them. It stretches those microscopic quantum ripples out to astronomical scales. Those tiny density variations became slightly denser regions of space, which exerted slightly more gravity, pulling in more matter over billions of years, eventually growing into the immense web of galaxies, galaxy clusters, and vast voids we see today. We are literally the macroscopic result of microscopic quantum uncertainty.
Now, the text mandates some deep scientific restraint here, and we need to be very clear about our confidence levels. Inflation is a breathtakingly elegant framework. It has significant observational successes that match the CMB data, but the exact physical mechanism, the specific quantum field that drove inflation and then stopped, remains completely unknown. It is a leading theory, not a closed case. Some versions of inflation predict primordial gravitational waves echoing through the universe that we haven't found yet.
That is crucial context. Science must remain comfortable with the unknown. And speaking of the unknown, that brings us to the second invisible pillar of our modern architecture, dark matter.
Let's talk about why we needed to invent dark matter. If we look at spiral galaxies spinning like our own Milky Way, the stars at the outer edges are moving much, much faster than they should be based on the laws of gravity. If the only gravity holding the galaxy together was coming from the visible matter, the stars, the gas, the dust we can see of those outer stars should be flung out into deep space. The galaxy should literally tear itself apart.
And it was brilliant astronomers like Vera Rubin who meticulously mapped these galaxy rotation curves in the 1970s, proving mathematically that there must be an enormous amount of unseen mass providing the extra gravitational glue to hold these galaxies together. And it's not just individual rotation curves. We see the need for this unseen mass everywhere. We see it in how massive clusters of galaxies move around each other. We see its imprint in the acoustic peaks of the cosmic microwave background. We see it vividly in gravitational lensing, where the immense mass of a foreground galaxy cluster bends the light of a background galaxy. The optical bending is far more extreme than the visible matter can account for.
But this matter is completely alien. It doesn't emit light, it doesn't absorb light, it doesn't reflect light. The text describes it as non-baryonic. I want to unpack that term because it's the key to why it's so ghostly. Baryonic matter is what you and I are made of: protons, neutrons, electrons. Baryonic matter interacts with the electromagnetic force. That's why you can touch a table. The electrons in your hand are repelling the electrons in the table.
But non-baryonic dark matter lacks the ability to interact with the electromagnetic force entirely. It only interacts through gravity and perhaps the weak nuclear force. You could have a dense clump of dark matter pass straight through the room you were sitting in, straight through your body, and you wouldn't see a thing. You wouldn't feel a physical impact. You would only feel a microscopic, localized gravitational tug.
And despite decades of searching with the most incredibly sensitive, deeply buried laboratory detectors on Earth, trying to catch a single particle of dark matter interacting with a regular atom, its exact particle identity remains a total mystery.
It does, which leads to a very natural skepticism.
Yes, let me offer the obvious, necessary pushback here. If we can't see dark matter, if we can't catch a particle of it in a lab after decades of trying, how do we know our foundational map of gravity isn't just fundamentally broken? Aren't we just inventing invisible ghost matter to make our equations balance? That sounds remarkably similar to the ancient astronomers inventing epicycles to force the planets to move in perfect circles. What if Einstein was just wrong at galactic scales and we need to modify our equations of gravity?
It is an excellent mathematically valid question. And modified gravity theories like MOND or modified Newtonian dynamics have been and continue to be rigorously tested by physicists. The problem is that while modifying the equations of gravity might successfully fix the rotation curve of a single galaxy, it generally fails to explain the rest of the overwhelming cosmological evidence. An alternative theory of gravity can't just solve one anomaly. It has to simultaneously explain the severe gravitational lensing, the chaotic dynamics of colliding galaxy clusters, and the specific temperature ripples in the cosmic microwave background. Right now, a cold, non-baryonic particle of dark matter is the only framework that elegantly fits the entire massive network of independent observations. But you are right to be skeptical. The door is not closed, and the search continues.
So dark matter is the unseen gravity pulling cosmic structure together. But in the late 1990s, we discovered a third invisible force doing the exact opposite: dark energy.
Astronomers were conducting a massive survey of distant Type Ia supernovae. These are exploding white dwarf stars that act as standard candles, meaning they explode with a known consistent brightness, allowing us to measure vast cosmic distances very accurately. The goal of the survey was to measure exactly how much the collective gravitational pull of all the matter in the universe was slowing down the expansion of space.
Right, because everyone logically assumed the expansion was slowing down. It's simple physics. If you throw a ball up into the air, the gravity of the Earth pulls it back, slowing its ascent. All the galaxies pulling on each other should be breaking the expansion.
But the supernova data showed the exact opposite. It was a complete shock to the scientific community. The expansion of the universe isn't slowing down at all, it is accelerating. The galaxies are flying apart from each other faster and faster every single day.
It is as if you threw that ball up into the air, and instead of slowing down, it suddenly hit the stratosphere and rocketed off into deep space, accelerating all the way. Something invisible, some inherent property of space itself, is pushing reality apart.
We call that something dark energy. In the standard model of cosmology, it is often represented as a cosmological constant. This was a mathematical term Einstein originally put into his equations, then famously retracted. But it implies an inherent energy density associated with empty space itself. As the universe expands, there is literally more empty space. More space means more dark energy, which drives even faster expansion, creating a runaway accelerating effect.
And when you combine the measurements of the CMB, supernovae, and galaxy distributions, the cosmic energy budget is staggering. It's deeply humbling. Ordinary baryonic matter, every star, every planet, every nebula, every human being, everything we have ever touched or interacted with, makes up roughly 5% of the universe. Dark matter accounts for about 27%, and dark energy makes up roughly 68%.
We live in a universe dominated by the dark sector. As the text acutely notes, the names dark matter and dark energy are really just labels for our ignorance as much as our knowledge. We observe their gravitational effects unequivocally on a cosmic scale, but their fundamental physical nature is entirely unresolved.
With all this dynamic expansion, this massive invisible conflict between dark matter pulling inward and dark energy pushing outward, the universe is constantly, relentlessly changing. But that brings us to a deeply philosophical question about the nature of change. Why does that change only seem to happen in one direction?
If you look closely at the fundamental, microscopic laws of physics, Newton's laws of motion, Einstein's relativity, even the equations of quantum mechanics, almost all of them are perfectly time reversible. The math works equally well playing forward or backward. If you watch a video of two billiard balls colliding on a table and there's no friction, you can't tell if the video is playing forward or in reverse. The physics are perfectly valid either way.
But the macroscopic world, our everyday physical reality, absolutely doesn't work like that. If you watch a video of a glass shattering on a tile floor or a drop of milk swirling and dissolving into a cup of black coffee, you instantly know if the video is playing backward. You cannot unshatter a glass. You cannot unmix the coffee. The change is strictly one way.
And that macroscopic irreversibility arises from statistics and the profound concept of entropy. Entropy is essentially a measure of the number of possible microscopic arrangements of a system that look the same on a microscopic level. Think about the glass. There is only one specific way to arrange the molecules to make a pristine, unbroken, highly ordered glass. It's a state of low entropy. But there are trillions of chaotic ways to arrange the shards of a shattered glass on the floor. It is a state of high entropy.
So, governed purely by probability, systems naturally and overwhelmingly evolve from rare, highly ordered configurations toward much more common disordered configurations.
Exactly. The thermodynamic arrow of time. The reason heat always flows from a hot object to a cold one, the reason structures decay is entirely dependent on the fact that our universe began in an extraordinarily rare, highly ordered, low entropy state at the Big Bang. We are simply riding the cosmic wave of increasing entropy.
But it goes deeper than just physics. It dictates our psychology. The reason we can remember the past but not the future, the reason we age, the reason we experience time as flowing forward is tied to this entropy gradient. Our brains require energy and create localized order, like memories, at the cost of increasing the overall entropy of the universe, like expelling heat. The psychological arrow of time aligns perfectly with the thermodynamic arrow.
Which naturally brings up the most fascinating, enduring concept in science fiction time travel. We just established that the arrow of time points strictly forward, but can we manipulate our speed along that arrow? Can we jump ahead?
A journey into the future is not fantasy. It is a proven, engineered scientific reality, courtesy of Einstein's relativity. If you build a ship and travel at a significant fraction of the speed of light, or if you spend a few years parked near the intense gravitational field of a black hole, the river of time flows much slower for you relative to the rest of the universe. When you return to Earth, you will have aged only a few years, while decades, or even centuries, will have passed for everyone else. You have effectively traveled into their future.
We prove this every day. The GPS satellites orbiting Earth are moving fast and experiencing slightly less gravity than we do on the surface. Because of relativity, their clocks tick at a slightly different rate than clocks on Earth. If we didn't constantly run Einstein's equations to correct for this relativistic time dilation, the navigation system on your phone would fail completely within minutes.
So forward time travel is just an engineering problem, but what about traveling to the past?
A journey to the past is an entirely different, vastly more dangerous beast. The equations of general relativity do theoretically permit bizarre geometries like traversable wormholes or closed time-like curves, which could hypothetically allow a path through spacetime that loops back on itself, enabling backward time travel. But generating these geometries requires extreme, likely impossible conditions. You would need vast amounts of exotic matter with negative mass energy to hold a wormhole open, and there is absolutely no evidence that such exotic matter actually exists in the universe.
And traveling to the past creates massive universe-breaking paradoxes, like the famous grandfather paradox. If you go back and prevent your grandfather from meeting your grandmother, you were never born. But if you were never born, you can't go back in time to stop them.
Precisely. The logic collapses. And this is where the text again demands strict scientific restraint. Backward time travel via wormholes is entirely speculative. It is a mathematical anomaly in the equations, not an observed or even highly likely physical reality.
Speaking of speculative mathematics running wild, I have to ask about the multiverse. It seems you can't read a physics article or watch a sci-fi movie today without hitting the multiverse. We have eternal inflation models creating branching, isolated bubble universes. We have the many worlds interpretation of quantum mechanics where every single probabilistic outcome splits the timeline. We have string theory landscapes with 10 to the 500th power different possible laws of physics. Are we actually doing empirical science here, or are physicists just writing very complicated science fiction with math?
It is a vital distinction to make and a subject of intense debate within the physics community itself. These multiverse concepts are not just invented out of thin air. They emerge organically from pushing our best current theories to their absolute limits. If inflation is eternal, it naturally produces separated bubble universes forever. If you take the mathematics of quantum mechanics entirely, literally without inventing a mechanism for the wave function to collapse, you naturally get branching histories. But as the text firmly categorizes them, these are unconfirmed, untestable hypotheses. They're not established facts. We cannot directly observe these other universes. We cannot interact with them. If a theory cannot, even in principle, be falsified by observation, many argue it steps outside the bounds of strict science and into philosophy.
So why do serious physicists entertain them?
Because they might eventually sharpen predictions in our own universe or connect to testable physics. But the deeper, truly unifying goal of modern physics isn't necessarily finding a multiverse. The holy grail is finding a working theory of quantum gravity. We desperately need a new framework that finally reconciles the smooth, deterministic, geometric spacetime of Einstein's relativity with the chaotic, probabilistic, uncertain principles of quantum mechanics. The map is incomplete, and the edges are burning.
While theorists are searching for that elusive quantum gravity on chalkboards and supercomputers, observational astronomers haven't just been waiting around. Which brings us to the modern era, because over the last decade, our astronomical tools have quietly ushered in a revolutionary paradigm shift that most people haven't fully absorbed yet.
For the absolute entirety of human history, from the first hominid looking up from a campfire to the launch of the Hubble Space Telescope, our knowledge of the cosmos came almost entirely through one single method: observing light. We captured photons across the electromagnetic spectrum, visible light, X-rays, radio waves.
But on September 14th, 2015, that monopoly changed forever. The LIGO observatories detected a signal from deep space. But it wasn't light. It was a physical ripple in the fabric of spacetime itself.
Gravitational waves. Over a billion years ago, in a distant galaxy, two massive black holes spiraled into each other and merged in an unimaginably violent collision. The energy released in that brief fraction of a second was greater than the light of all the stars in the entire observable universe combined. But it was entirely invisible. The energy was released strictly as violent distortions in the geometric grid of space. Those space-time ripples traveled outward at the speed of light for over a billion years. When they finally washed over Earth in 2015, LIGO's incredibly sensitive laser interferometers felt the physical space of our planet stretch and compress by a fraction of the width of a single proton.
We didn't just see the universe, we felt it. I like to frame these new observatories not just as better, bigger eyes, but as entirely new sensory organs for our species. LIGO allows us to literally hear the gravitational vibrations of merging black holes and colliding neutron stars.
And we didn't stop there. In 2019, the Event Horizon Telescope collaboration, which synced a network of radio dishes across the entire globe to create a virtual Earth-sized sensor, achieved what was long thought impossible. They produced an actual direct image of the shadow and the glowing ring of incredibly hot accretion material around the supermassive black hole in the center of the galaxy M87. And in 2022, they did it again, peering through the dense dust of our own Milky Way to image Sagittarius A, the supermassive black hole at the center of our galactic home. We finally looked directly at the dark shore.
And in that exact same year, 2022, the James Webb Space Telescope successfully unfolded its massive golden mirrors a million miles away from Earth. Webb is another entirely new sensory organ. It sees the universe in the infrared. It can peer through dense, opaque dust clouds to reveal the hidden birth of stellar nurseries. It can measure the delicate atmospheric chemistry of distant exoplanets, looking for the signatures of water and carbon. And it can look so impossibly far back in time that we are now seeing the very first rapid, chaotic growth of ancient galaxies just a few 100 million years after the Big Bang.
Each of these instruments accesses a completely different layer of reality. Space-time ripples, global radio interferometry, ancient infrared heat. They're transforming abstract chalkboard mathematical possibilities into hard, testable, observable accounts of the physical universe.
Which brings us to the end of our deep dive, to the epilogue of the unfinished universe. Because despite all these monumental discoveries, despite mapping the cosmos from the Big Bang to the edge of black holes, the universe remains fundamentally, defiantly unfinished.
And it is vital to emphasize that this incompleteness is not a failure of science. Science is not a completed, static book that we are simply proofreading. It is an ongoing, active, deeply human journey driven by profound doubt and constant, ruthless revision. Some of our most cherished, beautiful models will survive the test of time. Others will inevitably be discarded and replaced by deeper truths.
We have to embrace the dignity of epistemological humility. We have to be comfortable admitting what we do not know. We don't know the particle identity of dark matter. We don't know the underlying mechanism driving dark energy. We do not know what sparked inflation. And a working theory of quantum gravity remains a massive, unresolved puzzle that continues to mock our best minds.
But that honest, jagged frontier is exactly where science is most alive. Acknowledging our ignorance is what protects genuine wonder from collapsing into comfortable wishful thinking. Our species is incredibly small, our neurology is profoundly local, and our time in the universe is fleeting. Yet, through the rigorous collective application of evidence and reason, we get to participate in a story that spans the entirety of cosmic time.
And that serves as a direct call to action for you, the listener. Don't just take our word for it. Engage with the actual rigorous science. Read the respected peer-reviewed literature. Go visit a local observatory or a planetarium. Look through the incredible open-source mission archives and scientific data that space agencies make available to the public. Compare the sensational clickbait claims you read online with the hard observational evidence.
Let wonder spark your journey, but always, always let rigorous observation guide your path. The universe is not a puzzle made for our convenience.
No, it absolutely isn't. And that brings me to a final thought I want to leave you with, building on the idea we started with that the universe doesn't owe us an intuitive explanation. If our intuition evolved purely to survive slow speeds, weak gravity, and short distances on a warm rock, perhaps our generational struggle to unite quantum mechanics and gravity isn't actually a failure of our mathematics. Perhaps it is simply the ultimate hard boundary of our primate neurology. We are trying to visualize dimensions, geometries, and states of reality that the biological hardware in our skulls was never physically built to comprehend. Maybe the universe is just waiting for us to evolve a completely new way of thinking entirely. Something to ponder the next time you find yourself alone in the dark under a canopy of stars. The experiment continues. Keep looking upward.